All right, so you probably had this happen before. You buy some water and water bottles for an earthquake kit or some kind of emergency situation, or maybe you just bought them for the weekend and then you forgot about them for a few years. And when you look at them next, they kind of look like this. They are, well, that used to be round and now it's kind of slender. It has lost some weight. The bottles look like they've been squeezed. Now, what has happened here? Has the plastic stretched out, the way your socks, they fit when you bought them and now they're too loose because you've run them through the wash too many times and the elastic's gotten worn out? Is that what's going on? Or is there actually water missing from the bottle? Well, there's one way to find out, and here it is. If you look over here, see it says, try to get this so it's not in the glare, 237 milliliters. Let's see if this still has 237 milliliters. So I'm going to open this up. I'm going to open it up and start pouring, and hopefully not so much spilling. So I'm going to pour the first bits in here. Slowly to the top. Because if you overshoot, that's a pain. Okay, so that's 100. So it had 100 milliliters, that's for sure. Let's pour another. Just turn it so you can see the 100. There we go. Gotta always remember. There you go, that's 200. Put that in here. Yeah, now I didn't want to use this thing because those numbers on the side of a beaker are usually not as accurate as they are on the cylinders. So let's just dump the remainder. Get every last drop out of there. I think we got every last drop. And this is now empty. And let's see what we have here. Is it 237? Actually, no. As you can see, it's not even 220. It's about 218. So clearly about 20 milliliters of water disappeared from the bottle while the cap was still on. Now, how's that possible? I mean, these things are sealed. There is nothing coming out of here. How is the water getting out? Well, to answer that question as to where the missing 20 milliliters of water went, I will have to see you in the next shot. So we've established that the water is leaving the water bottle. The bottle is not getting looser, the water is leaving it. So the question is, how does it get out? How does a little water molecule get out of a bottle like this? Well, one thing to pay attention to is this does not happen with glass bottles or metal bottles. Somebody's got a cellar full of fine wines and they forget about a wine for years. It's not like they come in there and there's now a half a bottle of fine wine. So why is the water getting out of this when it doesn't get out of glass or metal containers? Well, glass and metal are network solids like this. Now, by the way, this is diamond, but I've got an organic model set, so I can't make glass. I can make diamond. But you can see the point here. The water is not going to be able to find a way through a matrix of this. But plastic, the most common plastic for water bottles is something called polyethylene terephthalate. And here I have it. It's right here. And what this is made up of is repeating units. This is a polymer. So you get repeating units of ethane and a benzene ring and an ethane and a benzene ring, and it repeats and repeats and repeats in these long strands, that millions of units long. And they're all, when they're made, when the chemicals come in contact with each other, they bind into these long strands, and they're just kind of every which way. We can sort them out a little bit, but basically what you have is kind of a chaotic net of polymer fibers. And like a net, small objects can get through. The sardine might escape from a fishing net that catches a tuna. So the water molecule is able to find gaps and get through and get out. Now, they could solve some of these problems by simply making it thicker, making it so that those gaps are more like tunnels that the water needs to get through. That would slow down the process. But there's always going to be little openings. It's not a complete network of atoms. Now, then the question is, okay, so the water can get out. Well, how come air didn't come in and take its place? How come the water got out and then the outside air pressure just crushed it because there was less in there? Well, there's a reason why air didn't get in. So a water molecule is actually smaller than an air molecule. And I know you're looking at this and saying, wait, no it isn't. Well, this is just a model. This is just a model to help you understand the structure of a water molecule. The set actually has little ones like this that make it, it's a little bit more accurate. It's what they call space filling. Even still, this is not accurate because hydrogen has only one electron, which is sharing with the oxygen. So that one electron from the hydrogen is basically in the electron orbits of the oxygen. So really what you have is something that's going to look like an oxygen with ears on it. That's what a water molecule is like. And that makes it a lot smaller than oxygen. I mean, water comes in at 2.75 angstrom, or 275 picometers. Oxygen is 3.46 angstroms, almost 3/4 of an angstrom bigger than the water molecule. More than 70 picometers bigger than the water molecule, and the nitrogen's even bigger. As a result, they might not be able to get through the same gap in that tangled mess of polymer that the water could get through. And if they can get through it, they certainly can't get through it as fast. So there's just no way that those air molecules are going to be able to get in as fast as the water molecules are coming out, and the network and the net effect will be less on the inside, less pressure on the inside, atmospheric pressure crushes it. So I hope that's been informative. If you have any questions, just put them in the comment page. I hope you've enjoyed this. Bye-bye.